All right, so let's get started with angular momentum. It's the observable associated with rotational symmetry. And we derived last time that the components of angular momentum, again, it's a vector of operators, one for each coordinate. These components satisfy the commutation relation that those T matrices satisfied that we looked at from studying the rotations in three-dimensional space. And we're just going to explore this object, this collection of operators, and see what we can do here. And there's two primary things of interest. There's the J squared operator, which is a scalar. And there is also, say, the Z component of angular momentum. And the idea is that these two things commute. So we could find simultaneous eigenvectors of J squared and JZ. So we can postulate for now that we have some eigenstates J comma M, where this labels the eigenvalues of J squared and this one labels the eigenvalues of JZ. So that's what we're going to do. And the thing to notice is that if we diagonalize these two guys, well, then J squared has JZ squared as sort of part of it. And this right here is the part that we need to figure out how to diagonalize. Find the eigenvalues and eigenvectors. Because if we diagonalize this part, then this is the only part that's left over from J squared that we have to deal with. And if you remember, this looks an awful lot like the harmonic oscillator Hamiltonian, which was h bar omega, and we wrote it in terms of these q hats and p hats, like that. I believe that's how we rewrote it. This is rescaled momentum and position coordinates. So you see it's a sum of two squares of operators, and this is also a sum of two squares of operators. It's quite similar to the harmonic oscillator. So we can use the same techniques to try to understand how to diagonalize J squared. And what we do is we introduce some raising and lowering operators, just like we did for a harmonic oscillator. We introduce some J plus or minus, which will be Jx plus or minus Ijy. And if you want to think back, it's just like we introduced A and A dagger for the harmonic oscillator. Quite similar. And so we're going to do the same sort of techniques that we used for the harmonic oscillator. We're going to apply these J plus or minuses to our eigenstates and see what the eigenvalues have to be. It'll look an awful lot like the harmonic oscillator did. And that's why we kind of skipped around in the book and did the harmonic oscillator first, because it's sort of an easier version of this. See, this is harder because we also have this JZ running around. So instead of having one label for our states, we have two labels corresponding to the two eigenvalues of J squared and JZ, which we're simultaneously diagonalizing because they commute. So you can use these commutation relations up here to derive a set of, and you'll be doing something like this on your homework, the last one, to derive a set of commutation relations between JZ and things like these J plus or minuses. It's just, you can expand J plus or minus and there's JY, JX and JY, and then you could just use these commutation relations here to figure out what all these are. So it's an easy calculation, just some algebra, and it's good practice. So you'll be doing that. For the homework. You can also rewrite the J squared. Of course, you can rewrite it as in terms of the J plus or minuses instead of this, by kind of completing the square, by factorizing this thing, just like the harmonic oscillator. So what you get is 1/2 J plus J minus plus J minus J plus, and this is how we factorize the harmonic oscillator Hamiltonian to A dagger A. Quite similar. And then there's of course the JZ squared that's left over. And you can of course invert this relationship and get expressions for J plus J minus. This is just J squared. This is J squared. These look quite the same, except this one's a +1. So, you can just show those using the commutation relations. And now what we can do is we can study here in green these eigenstates. We can try to figure out what happens to these eigenstates when we act with them with these various operators. So first of all, if we act with J squared, we know this is a positive operator, so it should be some kind of positive eigenvalue. And for now, let's just suppose we're gonna just suppose that the eigenvalue can be written as J plus 1. There's no particular reason for me to do this, except that's convenient later. So we're gonna just define J such that the eigenvalue of this J squared guy is this guy, so the eigenvalue. We could define it in some other way. We could have defined it as just equal to J, but then it makes things a little bit uglier later. So this is just like a educated guess, or an educated ansatz if you want. It's just we know the eigenvalue is going to be some number, so I might as well just call it J plus 1, J times J plus 1. You can do that. I'm free to do that. We'll see. It's just because it works out nicely later. And JZ, of course, is also going to be an eigenstate of JZ. So that we'll just label by M. That's the eigenvalue. And I didn't tell you what J and M are. They could be real numbers. Obviously these are Hermitian things, so they should be real numbers. This guy is going to be positive, so it should be a positive real number. But M could be anything, some real number. We're just going to have to figure out what they are. Remember, it's like the harmonic oscillator. You guess that you have an eigenvalue, and then you apply the raising and lowering operators, and you make an argument that the energy levels, the eigenstates have to be labeled by integers. That's what's going to happen here. Same thing's going to happen here. So what we find, for instance, is that if we take JZ and we act with it on J plus or minus, acting on one of these JM states, this is equal to, we can use the commutation relation between JZ and J plus minus to commute JZ plus the J plus minuses. So what we would get is J plus minus jz, right? That's this commuted through. And then you have to add back the commutator, which is the plus minus here. So it's plus minus j plus minus acting on jm. And you see now this jz can act on this m. And so what we find is that this is m plus or minus 1, right? Acting on j plus minus jm. So that means that this j plus minus jm is also an eigenstate of jz, but with one more or one less m value by an amount 1. So these are indeed raising and lowering operators for this m eigenvalue. And we also know that this j plus or minus, it doesn't do anything to the j eigenvalue. And that's also sort of easy to prove just by recognizing that j squared commutes with j plus or minus. So this is what it does. These j plus or minus raise and lower the eigenvalue of jz by 1. Okay, so that's the idea. And now, just as in the harmonic oscillator, we can try to get some conditions on these j's and m's. And the way to do that is to use, again, the idea of taking a vector norm and arguing that it's bigger than 0. So what we can do is look at j plus, for instance, acting on jm. Look at that, the norm of that vector squared. And j plus and minus are complex conjugates of each other, so this is equal to jm, j minus, j plus, jm. And now we can use one of these properties that you'll show on the homework, that one, or sorry, this one, I guess. So we can expand this in terms of j squared and jz, and those are those we know how to act those on the j's and m's, because these are the eigenstates of j squared and jz. So this is j squared minus jz plus 1, right, jm. So we know how that works. This is just j plus 1 minus m plus 1 from the jz's, and we can factorize this a bit to j minus m and j plus m plus 1. That has to be greater than or equal to 0. So what does it mean? If that's true, then MC must range from this M must be less than J, right? Because M can't be bigger than J, otherwise this will go negative. So that's one constraint. And then of course you can do the same thing with J minus JM. And it's the same procedure. This would just be J plus J minus. You would use this other identity up here. And you would get J plus M, J minus M plus 1. That's greater than or equal to 0. So this would tell you that M must be bigger than minus J. So if M goes below minus J, then you're in trouble, because then this will go negative. So that's not good. So we conclude from these two things that M runs from minus J to J. And so why is this, what does this imply? Remember that, again, just like the harmonic oscillator, the J plus or minus acting on Jm, those are also eigenstates of J squared and Jz. And they lower, the J minus lowers M by 1. So that's a problem, because what happens if we just keep lowering m until it goes below minus j? Or what if we raise m until it goes above plus j? That can't happen. So the only solution is if the ladder terminates, just like the harmonic oscillator. There should be some state where if you apply the j plus or minus operator that you just, so if you apply the, remember in black is the harmonic oscillator, we argue that there should be some state that if you apply the lowering operator to it, you get 0. Well, the same thing here, except now you have two ends of the ladder. It's a finite ladder where you can't raise the state above j and you can't lower it below minus j. So it's a finite ladder of states and you can't go above or below. So it's the same thing. There should be some integer. There should be some integer that if you take j plus and act with it on a state that's already been raised by an amount n1, then that should just give you 0. And there should be some j minus where if you've already raised the thing, lowered the thing by some n2, that should just give you 0 also. And these two things should satisfy m plus n1, right, is equal to j. So you can't go above j and you can't go below minus j. So if you take m and you subtract n2, that should be minus j. So that when you act again, you can't go below the minus j, and so you get 0. So this is the condition, and this is true for some integers, right? For some non-negative integers n1, n2. Just must be the case. It must be the case, just as in the harmonic oscillator, we argue that you just, in order for this to be a sensible eigenvector, right, to have positive norm, you can't raise and lower the eigenvalues indefinitely, eventually fall off the ladder, just like we had for the harmonic oscillator here in black, where we argued that there should be the bottom of the ladder. Now, in the angular momentum case, there's the top of the ladder too. You can fall off there also. So you can think about the eigenstates for the harmonic oscillator as sort of rungs on the ladder. You start with 0, 1, and so on. These are the energies. Here, it's the eigenvalues of jz, and they run from minus j to plus j. And you raise and lower by j plus minus. And here, we have raised and lowered by a dagger a. Same idea, except this ladder shoots off to infinity because you can have an arbitrarily large energy for the harmonic oscillator, but here you run off, you just fall off the ladder. And what's the last bit? Well, we can add these two together. These two equations that we have, we can add them together. And what we would find is m plus n1, right? Or sorry, I guess you can subtract them. Minus m plus n2 is equal to j minus j, which is 2j. And the m's cancel. So 2j is equal to n1 plus n2. So that means j is either an integer or a half integer, right? Since 2j is going to be an integer, it could be anything, some integer. So it could be, 2j is 0, 1, 2, 3, but j then must be either 0 or 1/2 or 1 or 3/2 and so on. Those are the only possibilities. And m must range from minus j to j. That's our ladder of states. So you see it has everything that we want from angular momentum. You see, for a fixed j, like a fixed j that gives you sort of the magnitude of the angular momentum. So j is 1/2, that would be like the spin 1/2 case. And M then labels the number of states that you get for that magnitude of angular momentum. So for 1/2, M would range from -1/2 to +1/2. Those are the two states of spin 1/2, right? The up arrow and the down arrow. And so there's this theorem that we've now proven that the possible eigenvalues of J squared are J plus 1 with J is equal to 0, 1/2, 1, 3/2, and so on. And M is equal to -J plus 1, and so on all the way up to J. So for a fixed magnitude of angular momentum, there's 2J plus 1 possible M's. And if you want, that's like the Hilbert space. That's the dimension of the Hilbert space associated with a fixed angular momentum. So we looked at spin 1/2. That was a fixed angular momentum of 1/2 for the spin magnitude. And then we had two values, +1/2, -1/2. That was a two-dimensional Hilbert space. For spin 1, there would be 2 plus 1, 3 states. So it would be a three-dimensional Hilbert space. And the basis vectors would be labeled by the M, which would go from -1, then 0, and then +1. And so for each J, you can think of a little ladder of M's, and that corresponds to all of the possible values of M that you could get for that fixed value of angular momentum. All right, any questions about that? I'll take a pause here because that's sort of important. This is really the main theorem of angular momentum. We see that just studying the rotation group, we were able to derive this sort of pretty profound result that, these angular momentum eigenvalues are quantized in this way into integers and half integers. And this is, very much related to the structure of the rotation group, right? That the SO3 has a double cover, the belt trick that I showed you. That's the reason why these J's break up into half integer and integer, eigenvalues, because everything we derived here comes from the commutation relations of these components. Everything we do here just comes from this. And this came from the properties of the rotation group, because we know that the J's are the observables associated with the unitaries that are representations of the rotation group. And those representations can be vector ones and spinor ones, and those are the integer and half integer angular momentum. But okay, any questions about this?
In simple harmonics, we just apply a plus, the raising operator or the lowering operator, right?
Yeah.
But in this case, we have to apply the product of JC with J plus or minus. We can't just apply J plus or J minus alone.
You can apply it alone if you want. The reason it's in the harmonic oscillator, what we did is we looked at a dagger acting on an eigenstate of H, where, you know, so we did do this, actually. We did this. We showed that this is still an eigenvalue. We showed that this is, you know, still an eigenvector of H. We did do that. So that's what we're doing here. We're showing that the J plus or minus acting on the eigenstate is still a eigenstate of Jz. Jz in this case is the equivalent of H in the harmonic oscillator. So we did do that. There's no difference. We're showing that J plus or minus J plus or minus acting on Jm is still an eigenstate of Jz. So if you want, this is like showing H acting on A, or A dagger acting on N is equal to a new eigenvalue, you know, A or A dagger acting on N. So it's the same thing.
Okay.
In fact, we did the same thing where we commuted H past the A and the A dagger and used the commutation relation between H and A dagger in order to derive a very similar thing to this. If you go back to the notes, you'll see it's the same. Okay, any more questions?
About that educated ansatz. So you said we could define the action of J squared and Jz in any way, and then we would just have to make sure that it satisfies the commutation relations.
Yeah, I could have called this lambda or something. And then everything would go through except, you know, these things wouldn't be as nice. I would have to put a lambda here, and then I'd have to figure out what lambda is in its relationships to the m. I wouldn't be able to factor it in this nice way. See, we picked j plus 1 because it ended up giving us this nice factorization. We were able to derive this condition. This condition is only possible if you originally defined things like this, but you could define it with a lambda, and then you would have some complicated inequality with square roots of lambda involved. But you would eventually realize that, you know, you could replace lambda with j times j plus 1. It would give you the same thing. It's just a lot more tedious. You know, it's unnecessary to do that.
Okay. Thanks.
It's just an eigenvalue. It's some number. We don't know what it is. So I might as well call it j times j plus 1. And then, of course, it worked out nicely. But you could do this whole argument, this whole chain of arguments again with just lambda if you want. It doesn't change anything except it makes these inequalities a lot uglier.
Well, I was just looking for the restriction that you could use to derive the others once you choose the answers. And you just said that's the commutation relations, right? So you just make sure that it satisfies the commutation relations. So
yes, these are the fundamental things.
Right.
The things in blue, those are always true. This is just, we just labeled the eigenvalue by this. We could have just called it lambda and then figured out what lambda has to be.
Okay.
Okay, more questions? All right, so that's good. So we want to now fully normalize things just like we did before with the raising and lowering operator. Remember that in the harmonic oscillator, when we had like a dagger acting on n, there was this normalization that we needed to introduce. You could do the same thing here using the same analogous arguments for the angular momentum, because it's exactly the same as the harmonic oscillator. It's just your ladder is finite instead of infinite on one side. And so I'm just going to write these down, the normalizations, because they're, you know, I'm just going to write down some, you know, facts that we sort of know now about these angular momentum eigenstates. First of all, it's also convenient to include not only the eigenvalues of j squared and jz, but there might be some other operators that commute with angular momentum, right? That could label, that we can have eigenvalues of those. So we'll group all those possible other eigenvalues by this tau. This is convenient when we do problems with specific Hamiltonians where we diagonalize the angular momentum piece, the rotational symmetry part, and then we have other stuff that's left over, like a principal quantum number that, you know, is related to the energy level that you're at. Some other eigenvalue that we might need, independent of the rotational part, the angular momentum part. So we'll just label all those by tau. But, you know, it could be anything, but it's just a convenient notation. Just to write out everything just completely so that we know what's going on. So j squared acting on tau, and I'll group the jm's together. So there's no, these are just the, I won't put a comma there, it's just more convenient that way. So that's by definition j plus 1, tau jm. Okay, then there's of course jz acting on tau jm. That just gives us m tau jm. Now the normalizations of the j plus or minuses are, well, they're a little bit annoying, but it's just like the harmonic oscillators, an equivalent of a square root business. Tau jm is the, it's going to be a square root here. It'll be j plus 1 minus m plus or minus 1 1/2. And whoa. And these guys get shifted by j, and then it's, I'll put the comma back, m plus or minus 1. So those are the raising and lowering. And then importantly, there's the ends of the ladder, that when you act on jj, that gives you 0. And when you lower beyond minus j, that gives you 0 too. And then of course, these states are going to be normalized. They're orthonormal. Like that. And that's our basis. We can use this as a basis to for diagonalizing any rotational piece that involves an angular momentum. Okay, so these jm's are a basis, right, for the Hilbert space associated with with angular momentum. So like spin 1/2, spin 1, and so on. Those guys form an orthonormal basis, and we can attach other quantum numbers if we want to it, which we'll see is important for like the hydrogen atom. Yep.
What do you mean the JJ state? Isn't it JM?
Yeah, but if M is equal to J, that's the JJ state. You go up beyond, if you boost M by 1, then it'll be 0, right? It's a ladder. It's a ladder of states. M ranges from -J to +J. And you can't go off, you can go off the ladder like that or like that. So J plus acting on JJ, that's 0 because you fall off the ladder. Yeah. J minus acting on J minus J is 0. Okay, so if you use these as a basis, then of course you can, use these as vectors. We already know some of them. So like, for instance, for J 1/2, M 1/2, that was our qubit. That was our qubit, and we could define a little 2-component vector. These are basis vectors for spin up and down. We also call these spin up and down. But you can do more now. Now you're equipped to do, for instance, J equals 1. If J equals 1, then M is equal to -1, 0, and 1. So that's a 3-dimensional Hilbert space. And so we could do things like use these properties to construct representations of, say, the angular momentum components. We know that, J prime, M prime, the matrix elements of JZ are going to be M. And we also know, for instance, the matrix elements of the raising and lowering operators, just from these guys, right? That's square root of J plus 1 minus M prime, I could call, and then I know that the J's have to be the same, and M prime has to be M plus, either M plus 1 or M minus 1, just from this. And so you can now use these matrix elements to like figure out what JX is. You remember these are related to JX plus IJY and so on. You can actually derive what the operators are on this J equals 1 Hilbert space. JX is this guy. JY is this guy. And JZ is this guy. This guy should make sense because like this guy is the M. These are just the values of M along the diagonal because we're diagonalizing JZ. And these guys are not diagonal because you can't simultaneously diagonalize JZ and these guys. That's the whole point, right? That's the reason why we diagonalize J squared in JZ. And you can get what these guys are by just looking at the matrix elements of J plus or minus, right? Because you can write JX and JY as just linear combinations of J plus or minus. And you can derive these, and you might wonder, are these look an awful lot like the T matrices. they're kind of like the TI matrices that we looked at for rotations. But remember that the TIs, they operate on real vectors in space. These guys, these J's, they operate on a different basis, right? They operate on this JM basis. They operate on 1, 1, 1, 0, and 1, -1. That's what the basis vectors are in this space. They're the angular momentum basis vectors. It's different from the actual XYZ components. But since these guys are generators of rotations, much like the T matrices are, they're actually unitarily equivalent. You can show that JI is just equal to a unitary transformation of the TIs. Because they must be sort of the same up to a unitary transformation, because they're the same kind of object. They're both generators of rotations. They satisfy the same commutation relations, right? As the T's. Remember up here, the fundamental thing is that the J's satisfy the same commutation relations as the T matrices. So that's kind of interesting. And important to consider. It's important to remember, again, the relationship between these states, which are space of angular momentum eigenstates, and then also the T matrices, which were telling us about the rotation, or the rotation group, the rotation matrices, which rotate real vectors in space. But they're related to each other because, again, these are all these things come from representations of the rotation group. Okay, any questions about that before I clear this stuff? So again, the important thing to note here is for each J, you get a ladder of states. And that's a little Hilbert space for a fixed magnitude of angular momentum, spin 1/2, spin 1, so on. And you can use these properties here to derive in that Hilbert space, like the matrix elements corresponding to components of angular momentum. So that's the idea. All right, I guess I'll clear this now. And now we'll talk about rotation matrices. So we dealt with the generators, the angular momentum pieces, but now let's talk about actual, full-blown rotations. And this is going to bring us back to these D matrices. And now you'll finally see where this notation comes from. Up here, you put the value of J, the magnitude of angular momentum, that subspace you're looking at. And here are the indices. This is an operator, and it's got indices labeled by the M's. So before we had M is plus or minus 1/2. That's a spin 1/2. So it was like a 2x2 thing, right? This guy had 2 values and this guy had 2 values, 2x2 matrix. This is the rotation matrix corresponding to some particular rotation in 3D space. This is our rotation. This is how those angular momentum states rotate when you have a rotation. So we already saw that for spin 1/2. And now using these angular momentum eigenstates, we can write out what this is. All this is Jm sandwiched between the unitary, right? That's the representation of the rotation. That's what the D matrices are. They tell you how within the subspace for a fixed J, how the Jm states rotate under this unitary, which is a representation of some actual rotation in 3D space. And just like the unitaries, these D matrices will inherit the properties of the rotation group. So we know that we had, for two different rotations, right, that the unitaries, they satisfy this guy for the vector representation, and otherwise, if we combine rotations, we can get a stray minus sign that pops up. Those are the spinor representations of the rotation group. Well, same thing happens with the D's, of course, because they're just matrix elements of these same unitaries. So D, J, M prime M of 2. The reason I write R2, R1 is because first, you know, it's like operators. You act with this first and the other one second. So first R1, you apply R1, then R2. So in general, then we would expect that these properties get inherited. So, you know, in principle, we could get plus or minus, right? The matrix multiplication of the corresponding D matrices. That should be the case. So let's try to see for which, when does this happen? For which values of J, right, do we get the minus sign? That's the idea. So we'll be able to show that the half integer J's are the ones that pick up the minus sign, the ones that have the spinor representation. So let's look at a particular rotation. We will look at this rotation that depends on theta and phi, which is, what you do is you take a rotation around the y-axis by an amount theta, fix the y-axis. So you can imagine starting something along the z-axis, you take around y, you rotate it by theta, that's that polar angle away from the z-axis, and then you rotate around the z-axis by amount phi. So that gives you sort of rotation for, you know, corresponding to spherical coordinates. Of course, this doesn't describe all rotations because we know we need 3 angles to describe a rotation, but this is a subset of the rotations that will help us see when do we get, you know, a vector of spinor representation. So that's the idea. So what's the unitary? The unitary, of course, is going to be the exponentiated angular momentum operators, because that's these guys. Remember rotations around a single axis, those are abelian subgroups, and by Stone's theorem, they're just these exponentiated angular momenta. See, so we have that. And that's nice because then we can actually calculate what this D matrix is, right? We just stick in this for up here in the unitary. Right, real easy because this is JZ, so that's already diagonalized. So that's pretty simple. So DJ M prime M of these rotations, that's going to be e to the minus I M prime phi. That's coming from this JZ here, right? This thing, when we act with on the left here, it just picks up an M prime because this is the eigenvalue of the JZ operator, so that's easy. And then we have something left over, which is the matrix element of, you know, the remaining piece, which is minus I theta JY. And this is not diagonal because remember we're diagonalizing JZ, so we can't diagonalize JY. This will be some matrix, and this is called the little d matrix. And this guy, of course, depends on M and M prime and J, and also, you know, it'll depend on theta. That's just what we call it. And those guys will satisfy a group property also, because that's the little matrix that corresponds to rotations around the y-axis. So that's good. Also note that this matrix, it's this here is a real matrix because JY, this guy is real because JY is equal to minus I over 2 J plus minus J minus. That's just what it is from the definitions of J plus and J minus. And these guys are the raising and lowering guys. So they have just real eigenvalues, right? Because they just raise and lower m by 1. And so the JY is always going to be sort of pure imaginary. We already saw that before. I guess I erased that, but we wrote down JY for the J equals 1 subspace, and we saw I had a bunch of I's in it. So it's always going to be pure imaginary. So this is like a fun fact. And JY is going to be pure imaginary, and that I cancels this I right here. So this is always a real matrix. And so these D's, they have certain properties related to sort of the properties of this matrix, right? First of all, if the inverse of it, right? If we take theta to minus theta, that would undo the rotation. So this guy here, the properties of this e to the minus I theta jy, they transfer to properties of these guys, right? Because these are just the matrix elements with respect to this basis. So you can show, for instance, that dj, this little j, m prime m theta is equal to dj m prime of minus theta, right? That you can get by just taking the complex conjugate here of this thing. Then the m and m prime will flip around, and you'll get a plus I here, the complex conjugate, and so you can show this as a symmetry of these little D matrices. You can also show that the m's flipped and the theta flipped signs. You can also show that this guy is minus 1 m minus m prime minus m prime minus m j theta. And that's some more properties of this D that you can show. Again, you can do all this by just combining the properties of this exponentiated jy with how these jm's act on it. So you can also show this. Maybe I'll show how to prove some of these things more in recitation, but these are just some properties of these D matrices. So what about this whole idea of spinor versus vector? Well, we can see how that works by just studying the D matrix, right, for rotation by 2 pi. We can look at j m prime u corresponding to a rotation around the z-axis by amount 2 pi. And now this is really easy because this guy, right, that's just the exponentiated jz operator. So that just gives us e to the minus 2 pi I m. And then it's diagonal in the m's because everything's already in terms of the JZ basis. So it just gives you this. Well, then if you think about it, right, these little m's, they range from minus j to j, right? So if j is half integer, then the m's are half integers, and vice versa. If j is an integer, then the m's are integers. So there's two possibilities here. Either this just doesn't pick up a minus sign and this just becomes 1. That's when m is integer. Or you pick up a minus sign when m is a half integer. Right? And this must be true if the corresponding j's are either integers or half integers, right? Because both m's and j's are either half integers or they're full integers. So, so that's how you know. That's how you know that when m is a half integer, a rotation by 2 pi will pick up a minus sign. So it'll get this. You'll have this spinor representation when m is half integer or j is half integer, and those are the fermions. Those are the particles with a half integer angular momentum. And these guys are the bosons, the ones with the integer spin. So, okay. And to see the group part, you remember that spinor versus vector had to do with these unitaries? Well, we can see that, we can write it out that way if we look at rotations by theta 1, theta 2 around some direction n hat. Then the combination of theta 1 plus theta 2, right? That's going to be, that rotation is just this guy. It's n hat dotted into the angular momentum. And of course, for any two angles, I can always write them as some angle between 0 and 2 pi, and then some integer number of 2 pi's, right? But you can always write it like that with n some integer. Right, if theta 1 plus theta 2 is over by an amount 2 pi, then you just, that's the integer plus theta, that amount that's between 0 and 2 pi. So then I can write this, right, as e to the minus I theta j dot n hat, and then e to the minus 2 pi I n j dot n hat. And there's nothing special about n hat. So this guy, this operator, 2 pi I n j dot n hat, it's the same as this guy, right? This is e to the minus 2 pi I jz. So the only difference with this guy is there's an integer n, and it's like now, a rotation around an arbitrary n hat, but that doesn't really change anything about the value of it, because by symmetry, of course, we could choose our n hat to lie along the z-axis, and this would still give you the same value here. So there's only two possibilities here. Either you get this guy, and this is just the identity, e to the minus I theta j dot n hat, and that's for integer j, or this guy picks up a -1 to the n, right? Because there's just this extra n. So if we stuck in an extra n here, right, then this would become -1 to the n. That's the only difference. And so when you have a half integer j, then you can pick up a minus sign. So when you combine rotations, right? When you combine rotations like this, you can pick up an extra minus sign when you have half integer j. And that's exactly like the statement here, that when you combine two rotations, the combined unitary can pick up a minus sign if it's in the spinor representation. That's explicitly showing you how that's the case for an arbitrary rotation around n hat. If you combine the two rotations, the combined rotation, which again, it would just be by theta, right? If you take theta 1 plus theta 2, and then whatever that total angle is, it's, you know, this angle theta modulo 2 pi, because the 2 pi rotations don't count. That brings you back to the same place. So that gives you this factor. And this, the key part is that when you have integer j, then these exponentiated operators behave just like rotation matrices, that, you know, the factors of 2 pi don't matter at all, right? But if you have a half integer j, then you're in the spinor representation, and the factors of 2 pi can be identified. You can have a representation that picks up a minus sign when you rotate by 2 pi. And that's that bell trick thing. So now it's sort of, hopefully it's all starting to connect in your head that it's all really the same thing. We're just repeating the same idea over and over again, but using different notation for it. But yeah, that's the idea here of these vector and spinor representations of the rotation group. This is how it plays out for rotation about an axis. Any questions about that? No? Okay. So if not, we're gonna make another. So I'll do more of this in recitation. And I think it's kind of important. It'll be important for the homework, but I want you to practice. This is more like, it's good to practice with these D matrices. It's a little too tedious to do in class. Plus, it's also not that important because conceptually, all you're doing is just studying this object, right? You're just studying this for a particular unitary operator, which is this one. You know, so it's not particularly interesting from a conceptual point of view. These two things are the only things you need to know. We've spent a lot of time developing these eigenstates, understanding what they are, where they come from, their properties. And we spent a lot of time, you know, talking about components of J. And so that's all this is. These are just the exponentiated J operators sandwiched between these eigenstates. So, I mean, of course, you know, there's a lot of tedious math you can do with them, but again, that's will be left for homework for the most part in recitation. I'll show you how to derive some of these things maybe. But okay, before I let you go here, the next couple of minutes, I want to, let me clear this. But any more questions about this kind of stuff?
You said you're going to go over in recitation, though, a derivation of those things. So
I'll go over properties of these little d's. Yeah.
Okay. Very good.
But again, you should at least, when you see this, you know, not be worried there's something weird. It's just exponentiated jy, which we studied a lot. You know, you can write this in terms of j plus and j minus and so on. And we studied these guys a lot. And so these are just the matrix elements of those exponentiated operators. That's all it is. But yeah, we'll look at it in recitation.
Okay.
But I don't think conceptually it's very interesting. These are just how you rotate the JM states. That's what this is.
Yeah.
All right, so I'll clear this now. So the next really important thing conceptually is the idea of orbital angular momentum. And that's the angular momentum you're probably more familiar with from classical mechanics, right? We know that in quantum mechanics, particles themselves, they have an intrinsic angular momentum, or, you know, a spin. But there's also an angular momentum associated with, you know, motion in space. And for that, we're going to have to go back to wave functions and sort of the coordinate representation. So suppose we have a spatial wave function, right? Psi of r. if we have a rotation, then we know that the rotated r vector, right, would have components x prime, y prime, z prime. If we rotate around the z-axis, then this doesn't change, but in principle, you could have x sine phi plus y cosine phi, x cosine phi minus y sine phi. This would correspond to taking our r and rotating it around the z-axis by some amount phi. That's a rotation like that. So if we rotate the coordinate, then what happens to the wave function? So in principle, we might wonder if when we rotate our coordinate system, does the wave function change? Well, in general, we might expect that it could pick up a phase. We see that it won't, but it could in principle. And in general, the rotated wave function should look like this, right? It should be the original wave function at the location where we undid the rotation, right? That would be the wave function evaluated in the rotated frame. You always need this inverse, much in the same way in translations. When you translate a system, right? If you have some wave function that's like peaked at the origin, we already discussed this once. But if you translate this by an amount a to this new function, it's peaked around a, the new function is the old function, right? Evaluated at x minus a. Because this has if the green guy has a peak at 0, the original guy has a peak at 0. The blue guy has to have a peak at a. So if you stick in a here, that'll be the original function evaluated at 0, which is where the peak is. So it's the inverse. It seems to confuse people a lot, that when it's in the argument of a function, when you rotate or translate or do anything, you have to undo the rotation or the translation inside the argument. So it's x minus a and the reverse rotation of the coordinate. So yeah, just something to think about.
Could you repeat that, please?
Well, I don't know how to explain it. I mean, so if you rotate your coordinate system, then the wave function in that rotated frame is the original wave function evaluated at the inverse rotation operating on the coordinate. Much in the same way, if you translate your system by an amount a, then your translated wave function is the original wave function evaluated at x minus the translation. Because that's the way, I don't know, that's the way the transformations work, right?
It makes sense. I follow. I follow now.
Yeah. It's just, so I don't know how better to explain it. It takes a while just to think about it. When you rotate something, how would you rotate the argument of the function? You have to undo the rotation to get the right place to evaluate the function in the rotated frame. But I think the best way is just by drawing analogy translations where the same thing happens. The original function, if it gets translated, that's this guy. That function is the old function evaluated at, x minus the translation. So it's because now you're here and you have to undo the translation to figure out what the value is with respect to the old function. Same thing here. If you rotate everything, you have to undo the rotation to evaluate the function. Maybe someday I'll think of a better way to explain that, but that's what it is. Okay, so what are we going to do now is we're going to see that this is not here. There's no phase. You don't need to worry about the wave function picking up some random phase. And the way you can do that is you can think about the r vector. Now this is the position operator. And we can think about its components, R sub k, where, you know, this is x, y, z. This is a position. It's the actual coordinate that you measure. And you can think about how this acts on a unitary, a representation of some rotation. This is a rotation now. And this is the position component, x, y, z. How that acts on one of these pseudo eigenkets, a rotated pseudo eigenket, right? We're going to take this unitary and act on it on the pseudo eigenket of position and see if we still get an eigenket of position. And I guess I'm out of time. That's what I'll show you, is I'll show you that that this rotated coordinate eigenket is still going to be an eigenket of an eigenstate of the position operator. So there's no extra funny phase that you develop when you do this. Because remember, what the psi is, of course, is just your psi state rotated by, this is the wave function, right? So this guy would be, psi prime would be the rotated coordinate. So u dagger, you're acting on the, so u acting on this r sandwiched with psi. And we'll just show that the u doesn't do anything funny. It just rotates the coordinate and that you don't pick up a funny phase. That's all we'll do. And because it doesn't pick up a phase, you'll see that angular momentum associated with actual motion in space will turn out to have only integer values of the angular momentum. So you can't pick up straight minus signs, but we'll see that later.
Well, I mean, I taught that today, you know, in my physics class. I was teaching the students by orbital angular momentum, and I was telling them about that. And it's just the same, just that we're looking more detail into it, you know, with quantum side of things. So
yeah, that's right. This is the angular momentum you're more familiar with. This is a sort of R cross P type of angular momentum.
Yep. So, but I like what you did here. I did, you know, of course I didn't get in this detail with them because they don't know like this kind of physics, but with you reminding us about that, having to get to the original for the rotation, that's pretty helpful.
Yeah, maybe there's some better way to explain it, but yeah, you have to, when it's in the argument of the original function, you undo the rotation. So it's the inverse always. Yeah.
That's cool.
But yeah, next time we'll see that orbital angular momentum, always integer. None of this half integer spinor representation stuff. That's only for, you know, the spin of fermions. It's not for motion, you know, the kind of angular momentum you're used to, the motion kind.